Let's discuss results for normal subgroups and homomorphisms. Hello everyone. First, let's discuss results for normal subgroups. One such result is that H is a normal subgroup of G if and only if G inverse HG, which equals the set of all G inverse HG where H is an H, equals H. Another result is that if H is a normal subgroup of G, then the order of G over H is equal to the index of G in H, which is equal to the modulus of G divided by the modulus of H if G is finite. Now let's move on to trivial normal subgroups and simple groups. If G is a group, then the set containing just the identity element and the set G are normal subgroups. These are called trivial normal subgroups of G. If G does not equal the set of just the identity element, and if there are no other normal subgroups, then G is simple. Next, let's define a group homomorphism. Suppose that G, which equals the set G with the multiplication, and H with the set H with circ are groups, and suppose that phi from G to H is a map. Then phi is a homomorphism of groups if phi of A dot B equals phi of A circ phi of B for all A and B in G. If, in addition, phi is injective, then phi is called a monomorphism. If phi is surjective, then phi is called an epimorphism. If phi is bijective, then phi is called an isomorphism. An isomorphism where G equals H is an automorphism of G. If G and H are groups, and if there exists an isomorphism phi from G to H, then G and H are isomorphic, and we denote this by G is congruent to H. Now let's talk about canonical projection. Let N be a normal subgroup of G, then the canonical projection of G onto H is pi from G to G over N given by pi of G is equal to Gn, which is a homomorphism. Now let's discuss some results for homomorphisms. Let phi from G to H be a homomorphism. Then phi of the identity element in G is equal to the identity element in H. And for all z an integer, we have that phi of G to the power z is equal to phi of G all to the power z. Also, ker of phi, which equals the set of all A in G such that phi of A is equal to the identity element in H, is the kernel of phi, and the im of phi, which is the set of all x in H where phi of A equals x for some A in G, is the image of phi, also denoted as phi of capital G.
As ever, thank you for watching.